Hello friends, in this video I'd like to solve the following problem from the Romanian National Mathematical Olympiad 2007 for 12th graders. Problem number 1. It's a nice problem for 12th graders. Let's see with a class or all continuously differentiable functions f from the interval 0, 1 into the set of real numbers such that f of 0 is 0, f of 1 is 1. We wish to find the minimum value of the integral from 0 to 1 of square root of 1 plus x squared derivative of x squared dx, where f runs all over the set capital C, so this class of our functions. We wish to find the minimum, and moreover we wish to find all functions f from this class realizing the minimum value. So here are my hints for this problem. It's all about Cauchy-Schwarz inequality, which states that if we take integral of some square of function g times integral of square of function h is always greater than or equal integral from 0 to 1 or some other interval, doesn't matter, of product of g of x times h of x, everything squared. And that holds for every continuous functions g and h. In fact, it holds for much larger class of functions, but we need only continuous functions. And moreover, very important, equality is attained in our inequality if and only if g and h are linearly dependent. So one function is the other function times some constant. You should consider the following functions. G of h equals the fourth root of 1 plus x squared times f prime of x. H of x equals 1 over fourth root of 1 plus x squared. And finally, the following facts which I wish to prove. I will not prove Cauchy-Schwarz equation inequality because it's too long for this video. It's a well-known fact, but lesser known facts. There is a function called area hyperbolic sine. It's inverse of hyperbolic sine, which can be given by this formula. It's a natural log of x plus square root of 1 plus x squared. Its derivative is 1 over 1 plus 1 over square root of 1 plus x squared. And we'll also use the fact that integral of 1 over square root of 1 plus x squared dx, this integral equals natural log of 1 plus square root of 2. We'll give this problem a try and I will see you in a minute. Okay, so maybe you know what, I will start with proving these facts which I stated here. Well, let's consider the first to be a definition or area hyperbolic sine, so nothing to be done for the first, but we can prove 2 and 3. Well, it's very easy. We just need to differentiate natural log of x plus square root of 1 plus x squared. So let's maybe prove of second point. Well, d over dx, area hyperbolic sine of x, it's the same as derivative of natural log of x plus square root of 1 plus x squared. And now we will use chain rule. Derivative of natural log is 1 over the argument. And now chain rule. Derivative of x is 1. Derivative of square root is 1 over 2 times square root. And once again, chain rule. Derivative of 1 plus x squared is 2 times x. Let's simplify it. It's 1 square is that, and for the second fraction, what do we have here? Well, 2 and 2 cancel each other out, and let's make a common denominator, 1 plus x squared under the square root. and here we have 1 plus x squared plus x, and denominators, this numerator and this denominator cancel each other out, and we have 1 over square root of 1 plus x squared. Very well, so it's proven. And now proof of third point. So we wish to evaluate integral from 0 to 1 of 1 plus x squared. Well, it's much simpler now, since we know the antiderivative of our integrand. We know that it's just natural log of x plus 1 over square root of x evaluated from 0 to 1. If I plug in 0, I have natural log of 1 plus square root of 2. And if I plug in 0, I have natural log of 1, which is 0. So it's proven. Very well. Now, our main result. We will consider now two functions. So consider two functions. G of h will be root of degree 4 of 1 plus x squared, f prime of x, and consider h of x, which is 1 over fourth root of 1 plus x squared. These two functions. Now, I will apply Cauchy-Schwarz inequality by Cauchy-Schwarz inequality. We know the following. Integral from 0 to 1 of g squared by g squared is just 1 plus x squared, so under square root, f prime squared dx. This times the integral from 0 to 1 of h squared. So it's root of degree 2, 1 plus x squared, is always greater than or equal. They are greater than or equal, what exactly? Product square of integral of product of these two functions. And if you take a look, product of g and h, it's just f prime of x dx squared. Okay, now, what do we get now? Well, our integral, we have integral from 0 to 1 of 1 plus x squared under the square root, f prime of x squared dx. Now, this second integral, this right here, it was evaluated. It's natural log of 1 plus square root of 2. What about the right hand side? Well, on the right hand side, we have an integral of derivative. So it's just f of x evaluated from 0 to 1. Very well. And now I will divide by this natural log. It's a positive number, of course, so I can safely divide. And what do I have on the right hand side? Well, notice that f of x evaluated from 0 to 1, it's f of 1 minus f of 0. And remember that in our class, every function f of 0 is always 0 and f of 1 is always 1. So it's 1. So it's 1, in other words. So now we know that it's greater than or equal 1 over natural log natural log of 1 plus square root of 2. Perfect. So now we have some type of inequality. So we predict that the minimum will be this number, but now we have to show that equality is actually attained. So the second part of Cauchy-Schwarz inequality is helpful. We know that equality is attained if and only if functions g and h are linearly dependent. i.e., our function g is some constant a times our function h. And let's see. What is g of h? G of h is root of degree 4 of 1 plus x squared times f prime of x, and that equals a, and h of x was 1 over degree of root of degree 4 of 1 plus x squared. And that means that f prime of x should be equal a over 1 square root of 1 plus x squared. And now we know the derivative is equal to this. When we wish to find our function f itself, and now my claim number 2 is helpful, because now we know that the derivative of this function equals 1 over square root of 1 plus x squared. So f of x equals a times natural log of x plus 1 plus x squared under square root, but remember, plus some constant b. Because we know that if two functions differ by a constant, they still have the same derivative. Okay. Now, what are values of of a and b? Well, I need a new page, so give me a minute. Give me a minute. Perfect. Well, remember, since f should be in our class C, f of 0 should be 0 and f of 1 should be 1. So now we have two equations, we have two parameters a and b, so we can compute them. Well, if I plug in 0, since f of 0 is 0, it must be that b equals 0. So one parameter is already known. And since f of 1 is 1, it must be that, well, what exactly? Let's put in 1. So we have a times natural log of 1 plus square root of 2, and that equals f of 1 is 1. So our parameter a is 1 over natural log of 1 plus square root of 2. And now we have our formula for our function. That means that f of x equals natural log of x plus 1 plus square root plus x squared under the square root over natural log of 1 plus square root of 2. And now you can leave it as that, but we can change the base of our logarithms. It's exactly the same as logarithm with base 1 plus square root of 2 of x plus 1 plus x squared under square root. And now we know two things. First of all, our minimum is actually attained for this and only this function. And moreover, our function, our minimum, equals this number. So you know what? Let's write it and let's finish our problem. So now we know that the minimum over all functions in our class variable c, better, equals 1 over natural log of 1 plus square root of 2. It is attained only for f of x, which is equal to logarithm with base 1 plus square root of 2 x plus square root of 1 plus x squared. And that is our result. That is our result indeed. Make a better ellipsis. Not exactly better, but whatever. Okay, that's our result. One more thing, because now we know that f of 0 is 0, well, f of 1 is 1. Is it continuously differentiable on the interval from 0 to 1? Yes, it is. It's in our class, so everything is satisfied and we have our answer. Very nice problem. And remember, keep in mind, it was given to 12th graders, high school students, not university students. Beautiful problem. As always, problems from various Romanian Olympiads are usually very, very beautiful and hard, as they should. Thank you for watching, and I will see you next time. Goodbye.